Welcome, and thank you for joining us for today's webcast, Measurement Traceability and Errors Related to Force Measurement, sponsored by Morehouse Instrument Company and TechBriefs Media Group. I'm Billy Hurley, Associate Editor with TechBriefs Media Group, and I'll be your moderator today. Our webcast will last approximately 30 minutes, and there will be a question and answer period at the end of the presentation. If you have a question, you may submit it at any time during the presentation by entering it in the box at the bottom of your screen. Our presenter will answer as many questions as possible at the conclusion of the presentation, and those questions not addressed during the live event will be answered after the webcast. Also, during the presentation today, we will present you with a poll question, which we invite you to answer at the appropriate time. In order to view the presentation properly, please disable any pop-up blockers you may have on your browser. At this time, I'd like to introduce our speaker. Henry Zumbrin is President of Morehouse Instrument Company. Henry currently teaches force and torque classes at the NCSLI Symposium, as well as at Morehouse. Henry is a Six Sigma Black Belt Lean Champion and is a technical advisor for NAPT. Henry has 17 years experience in force calibration. So now I'd like to hand the webcast over to our speaker, Henry Zumbrin. Henry? Henry, you there?
Yeah, hi. This is Henry Zumbrin with Morehouse Instrument Company. Thank you, Billy, for the introduction. I'm honored to be presenting this information to everyone. I'm so glad we have an audience interested in measurement traceability. I'm also known as this guy right here talking right now. For this webinar, the abstract is Metrological Traceability in relation to force measurement. We're going to discuss that. We are also going to discuss common force measurement errors and the importance of calibrating the instrument in the manner it is being used. Today's learning objectives are understand the metrological traceability hierarchy, identify potential force measurement errors. I'd also like to add that this presentation is available in PDF form on our website at www.mhforce/S NASA webinar PDF. On our current site, we put a pumpkin there, so it'll be easy to see. It's Halloween. Happy Halloween to everyone. So let's first discuss the 7 essential elements of measurement traceability. Number 1 is reference to International System of Units, SI. Number 2, unbroken chain of comparisons. Number 3, measurement uncertainty. Number 4, competence. Number 5, documentation. Number 6, calibration intervals. Number 7, measurement assurance. Number 1, SI units, the 7 essential elements. Per NIST SP 811, reference to SI units, the chain of comparisons must, where possible, end at primary standards for realization of the SI units. The SI base units are a choice of 7 well-defined units which by convention are regarded as dimensionally independent. These units are the meter, the second, the kilogram, the ampere, the Kelvin, the mole, and the candela. It's important to note that derived units are formed by combining the base units according to the algebraic relations linking the corresponding quantities. Force, in particular, equals mass times acceleration and is derived from the meter, the second, and the kilogram. So, number 2, metrological traceability. Property of a measurement result whereby the result can be related to a reference through a documented, unbroken chain of calibrations, each contributing to the measurement uncertainty. This is per the VIM section 2.41, which is the International Vocabulary of Metrology. Again, if you download this presentation online, there's a link there. The VIM is free to download from the VIM. It's from the BIPM. And it is free to download. So if we look at metrological traceability, it requires an established calibration hierarchy. If we look at this, the example of measurement uncertainty worksheet for primary standards, calibration of primary standard weights was performed by NIST. If we look at this, this is a sample CMC. We're going to discuss this in a minute. So, calibration and measurement capability, also known as CMC, is a per-point analysis. It represents the measurement process with the best test instrument and a repeatability done on a per-point basis with at least 3 runs of data. CMC is required for ISO IEC 17025 accreditation. On the Morehouse dead weight standards, the following was used to determine CMC. We used repeatability of the test instrument, otherwise known as TI. You'll see that abbreviated several places. In our dead weight machine, we used the resolution of the TI, and we used NIST uncertainty for the weights used at the point tested. This includes corrections for air buoyancy, stability, wear, and a local gravity correction. We had gravity determined on our site at 4 different locations, and we took the average. Number 3, if we look at the measurement uncertainties relation to measurement hierarchy, on the left you can see a pyramid. It starts at the bottom and it goes to the top. The largest uncertainties are with field measurements, and at the top is the BIPM, which have the lowest uncertainty. If we look at typical uncertainties for force measurement, NIST in this country has deadweight primary standards up to 1 million pounds of force. Their uncertainties at K equals 1 are typically between 4 and 5 parts per million. This depends on barometric pressure. They are currently, right now, they are redoing their system to go from 5 to 4, and it's all going to be dependent on what the barometric pressure is. Then you look at labs, primary reference laboratories. Those are such like Morehouse, ourself, where we have about an 8 part per million uncertainty. The next tier down, we're looking at accredited calibration suppliers. They typically run around 0.02% or 200 parts per million, followed by working standards, which is about 0.1%, and then the end for force is a field measurement. This is typically anywhere from 0.5% to 5%. If we break this down a little bit, we look at the first level, the BIPM. The BIPM is the highest level on the chain of traceability and where the 7 SI units are realized. From the BIPM, the international prototype of the kilogram, an artifact made of platinum iridium, is kept at the BIPM under the conditions specified by the first CGPM in 1889 when it sanctioned the prototype and declared. And an NMI. In this country, the United States, the National Institute of Standards and Technology, otherwise known as, commonly referred to as NIST, is the designated NMI. Primary Reference Laboratory, that's us, Morehouse Instrument Company. We are primary reference laboratories use deadweight primary standards, typically calibrated by NIST, and we use standards for force measurements up to 533 kilonewtons, which equates to about 120,000 pounds of force. The next tier down is the accredited calibration supplier. They use secondary standards. The secondary standards are defined as those calibrated by primary standards. Then we get to the working standards. Working standards and certified reference materials used in commerce and industry. Working standards can be either traceable to the secondary standards or traceable to primary standards, meaning if your lab's using a working standard, they may choose to have it calibrated to a more higher level of certainty by bypassing the accredited calibration service provider and using a primary reference laboratory. And finally, we get to field measurement. These are typically the material testing machines used for tensile, compression, fatigue, impact, rheology, structural, materials, or a range of other force applications. Measurement uncertainty. CMC is defined as calibration and measurement capability. It includes the following standard uncertainty contributors: repeatability, resolution, reproducibility, reference standard uncertainty, reference standard stability, and environmental factors. I sometimes call these 5 R's and an E. Pretty easy way to remember them. 3. Measurement uncertainty. Now, if we look at these 5 R's and an E, and we examine the CMC, the calibration measurement capability, using a primary standard, which was the third tier in the uncertainty chain, as the reference and how it affects the expanded uncertainty. If we look at this particular example, this is a load cell was tested in a machine at 10,000 pounds. Our CMCs are 0.0016%, and that is for a coverage factor of 2, which corresponds to approximately 95% probability, or 0.16 pounds at 10,000 pounds. If we look at the CMC using this formula here, which is actually the Welsh-Sather weight, and we look at all the percentage of contributions from everything, from the unit under test, resolution, everything else, we look at the standard, the reference standard, the uncertainty contribution is 14.43%. It's important to note that. If we go to the next slide where we're looking at this from the accredited calibration supplier with secondary standards, typically their CMC is 0.4% for 95% probability, coverage factor of K equals 2, or 4 pounds. If we look at everything for them using secondary standards, the percentage contribution to calibrate that same instrument when fitted through this Welsh-Sather weight equation is 95.74%. Now, if we compare Morehouse versus your typical accredited cal supplier, or if we compare primary standards, really, any lab using primary standards, NIST, there's other commercial labs using primary standards, versus the secondary standards that most accredited calibration suppliers use, when we look at this whole overview or whole picture of this, we see the expanded uncertainty using primary standards is 0.41 lbf at capacity. And we see repeatability, typically in dead weight frames with those low uncertainties. The unit under test is going to tend to repeat better. And we see repeatability of 0.057 lbf. So we look at this side versus the other side. The expanded uncertainty at 10K with a secondary standard, 4.03. And the repeatability for this was 0.379. Now, we did our own test. This test was done in-house. We took a load cell, specifically a Morehouse load cell. We calibrated it in our dead weight frame. Then we took it over and recalibrated it with a live class. We give force measurement classes, and with a live class, we redid this calibration, and they did their own repeatability study with a semi-trained technician in-house, and the repeatability was 0.379. Still, the expanded uncertainty was around 4.03 lbf. So this was an actual live demonstration performed in front of a class, and what we found was the expanded uncertainty when calibrated with primary standards is approximately 10 times lower than using secondary standards. Now, if the technician were better trained, maybe the repeatability number would go down. But if you look at the individual contributions, the repeatability number is not a high percentage of the overall contribution. In fact, it actually lowers it if we refer to the previous slide in the actual percentage. So what I've been going over some CMCs. What we have done, we've prepared a measurement uncertainty, calibration, and measurement capability Excel worksheet. If anybody needs help with budgeting CMCs for force measurement, this is available. It is free. We hand it out freely. If anybody wants it that's listening, just please contact info@MHForce and give us your name, your email, what you want, measurement uncertainty, and we will be happy to send you a copy. It will also be available on our new website launch, which should happen in the next few days. So at this point, I'm going to turn everything over to Billy. Billy's going to ask everybody a poll question, and we're going to figure out what to find the results. Thanks.
Thanks, Henry. So now it's time for our first and only poll question today. It will appear on your screen now. And the question is your calibration service provider meeting traceability requirements, which include properly reporting measurement uncertainty? And your choices here are A, yes, B, no, or C, maybe. And you can make your choice by selecting the appropriate button on your screen. Again, is your calibration service provider meeting traceability requirements, which include properly reporting measurement uncertainty? Yes, no, or maybe. And as you make your selection, I will hand the presentation back over to Henry Zumbert. Henry?
All right, thank you, Billy. As everyone's making their selection, here's what's important to note. If measurement uncertainty is not being provided by your service provider, there is no measurement traceability. How do you know how good your measurement uncertainty of your device is if the service provider is not telling you what their measurement uncertainty is? They may have a measurement uncertainty that's 4 or 5 times what you expect your device to be. So that brings us on to the fourth essential element of traceability, which is competence. The laboratories or bodies performing one or more steps in the chain must supply evidence for their technical competence. By documented proof, the service provider is accredited. The importance of competence. If the laboratory staff performing calibrations do not know how to calibrate a device, i.e. using improper adapters, not aligning the unit under test, UUT, properly, and improper loading procedures, are they competent? Can there be confidence in the reported results? How to provide evidence of competence? Well, we can do that by proof of training records, on-the-job training, OJT, and evaluation by management. This is still questionable as it is self-declaration. I can say I'm competent, but how do I prove it? Really, accreditation to ISO IEC 17025 is the best evidence available. Though, for those listening, I really believe the best evidence to prove competence is by calibrating an artifact with primary standards and then performing an in-house ILC by yourself against that artifact to ensure your measurement uncertainties are what they claim to be. And if we go back to that sheet that I offered, everybody can email us for a free copy. That sheet also does ILC testing and figures the EN ratio between the reference lab and the secondary or working standard laboratory. So that sheet is a valuable tool to help you conduct an ILC. Competence and measurement error. Examples of competence include using improper adapters when calibrating force instruments. Well, improper adapters can produce errors 10 to 20 times that of manufacturer stated accuracy. We're gonna see an example of that coming up shortly in force measurement errors. In fact, it's the next slide. The proper alignment of a UUT, unit under test, adapters, and proper methods for loading threads. These are all coming. All this is coming up in the next few slides. Misalignment, different hardness of top adapters specifically, and thread loading versus shoulder loading contribute to a decrease in the repeatability of measurement results, resulting in additional measurement error. So, repeatability and reproducibility tests, as well as proficiency tests, what we talked about in the last slide, are good methods for detecting measurement errors. So if we look at this is pretty common. Not a lot of people know about this. Manufacturers typically do not advertise this. This is a tension link. They are sometimes referred to as load links, dynamometers, or crane scales. If we look at the picture on the left, I call this slide loaded without the proper pin diameter. If you can see, there's still a lot of space in this instrument. So when we apply a force of 50,000 pounds to this instrument, which we think is, we know it's not the proper adapter, but somebody else could just throw a pin in there and load it. The output here on this particular instrument was 49,140 pounds. Now, if we look at the picture on the left in this picture, which I call loaded with the proper pin diameter, we have near full engagement. Well, that near full engagement is going to produce more strain or is going to produce actual more strain on the element, and the device, when engaged with the proper pin diameter, reads 50,000 pounds. This is important to note. There's a big difference here. You could put in Kevlar slings, you could put in different pin sizes, you could put in something else. You're going to get different results on this type of instrument. The manufacturer's accuracy specification on this particular instrument is 0.1% of full scale. So that leads me to ask everybody, what if you are using a device like this for critical weighing application? We had somebody come at a trade show and said, hey, we're weighing uranium with these things. I said, well, can you afford to be out 1.72%? Their answer was simply no. That gets us in a lot of trouble. So if we look at this, the out of tolerance versus in tolerance, there's a difference between loading with a proper pin size and loading without the proper pin size in this particular example of 860 pounds or 1.72% error at 50,000 pounds of force. So I must preface this, I must say, tension links of this design seem to exhibit similar problems. If you are unsure about this, this is something that you can easily check. You can test it. We can fabricate adapters. We have a full machine shop. We can fabricate the proper tension members, adapters. You can call the manufacturer. Typically, they don't publish this stuff online, but they will absolutely, in almost all cases, they have worked with us and they have given us sheets on what the proper pin sizes are for this instrument, or for these types of instruments. Again, most of them exhibit this error. If you're unsure, test it. The next potential measurement error. This is a misalignment test. We shot a video a long time ago, and I recreated this the other day in particular for this webinar. This is a misalignment demonstrating 0.752% error. The picture on the left is an S-beam load cell aligned in compression in our 12,000-pound dead weight machine. And the picture on the right is the same specimen, slightly misaligned. If we look at this, the output in the aligned machine is negative 1.96732 millivolts per volt versus negative 1.98211 millivolts per volt when it's just slightly misaligned. So if we look at our individual contributor sheet using that Welch-Satherthwaite equation again, if we look at the S-beam lower limit factor and we look at the column on the left where it's aligned, we do an ASTM E74 calibration, determine the lower limit factor. There's some information about that on our website. And we determine the expanded uncertainty for that measurement is 9.95 pounds force. If we go over to the right, we misalign. We put an error in. Say somebody's out in the field or somebody's making a measurement and they're not testing right, or somehow they have this same device misaligned. We know we've quantified that error in our test. So if they're out there thinking they're calibrating something to 9.95 pounds of force, and they go out there and they accidentally misalign the specimen, we're showing the expanded uncertainty would go from 9.95 to 85 pounds just from that slight misalignment on that S-beam cell. Now another potential measurement error is the different hardness of top adapters. This was an actual example where a customer brought in a 1,000,000-pound load cell from us. I was the one doing the calibration at the time, set everything up, loaded it to capacity, which was 1,000,000 pounds, and observed a 1,500-pound difference. Well, this is not typical of something we see every day. We check our records. We check the previous cal. ASTM actually says, gives us a criteria in one of their sections. They give us criteria for stability of 0.16% of applied, and this was higher. So we found ourselves asking some questions, particularly, is this a stability issue? Is the load cell bad? Did the meter go bad? Or is this an adapter issue? So we did our checks with simulators and everything else and decided, hey, the best thing to do right now is call the customer. Called the customer. They informed us about 6 months ago they changed top adapters. I said, oh, really? So would you mind sending back the original top adapter that was used the last time it was calibrated? Do you want to send that back? And they said, yeah, we'd like to send that back and see if that is the culprit. So when we used the new adapter, the load cell read about 180 pounds high. That's pretty typical. A year or two between calibrations, 180-pound difference at 1,000,000. That's not too bad. So basically, the adapters do make a difference. When that person was using the other adapter instead of the adapter that they had originally thought they were using, they thought their expanded uncertainty was 269 lbf, but using that other adapter and running it through the Welch-Satherthwaite, the difference, when they switched adapters, their expanded uncertainty became 1,490 pounds. That is very significant, and they did not know the wiser. So loading through different threads. This is quite common. I have a few examples of this. I actually have 2 examples right now. In our class, we give more. Below is a test we did with 2 different adapters, pretty standard cell. We loaded it to 10,000 pounds, called the customer, asked them, they did not send adapters, asked them what they wanted us to do. They instructed us, do it how you normally do it, so that was pretty vague. We documented everything. We did tests, actually sent them all the information, and then we noted on our certificate exactly what we did, and that's documentation. So if we look at the picture on the left, we loaded the load cell, this particular single column, I believe a single column cell, with 1.5 inches of engagement, and got an output of 10,000 and 1.5. When we loaded it with the adapter on the right, the far right, which is a 1/2 inch adapter, we got a output of 9,942.3 lbf. There was a difference between loading this cell between these 2 different adapters of 59.2 pounds. Now, a typical cell like this, the expectation is around 0.025%. The error on this measurement was over 5% on a device expected to be better than 0.025%. I have to ask, how are you or how are your devices being calibrated? Do you specify when you send them to the manufacturer? Do you send the appropriate adapters for them to replicate how you are using it? Now, if we look at this, this is a cell, we sell several of these, this type of load cell. It's a shear web type cell. If we look at the graph here, that's the same scenario, loading with different thread depths. The top light gray line in this graph shows the difference in output when loading a shear web load cell at different thread depths, whereas the bottom darker line shows the difference in output when loading against the shoulder. So what am I saying here? I'm saying if you don't have an adapter locked in and you load against the shoulder, you can get pretty consistent measurements. Whereas if you're just varying the thread depth on one of these cells, you could have an error magnitude of 0.25 to 0.05% difference, depending on the output of the cell. This one, if you look to the right, we had about 0.009 millivolts per volt, which on a 2 millivolt cell is about an 0.05% error. So, conclusion on this one: the only way to produce repeatable results 100% of the time is to lock an adapter into place against the shoulder on the load cell. This adapter then becomes an integral part of the load cell. This lockdown adapter will eliminate all of the errors shown in the above graph due to different thread depths. A Morehouse threaded adapter with jam nut permanently locked into the load cell will eliminate the error shown in the above graph and allow the end user to accurately duplicate the results created from the calibration report. When we do these, we typically preload a cell to 100, 120, 140%, and then we hand tight them in, or we use a spanner wrench. We lock them in. They're to remain locked in place. If a tech is out in the field and takes them out, they're voiding their calibration, or they're really increasing their measurement uncertainty by an amount of up to 0.05% or more. Measurement error information. Now I've skimmed the surface on this. We have lots of examples. If you want to learn more in-depth knowledge about force measurement, you can visit our website at www.mhforce.com. It's customer education. We also offer 2, 3, 4, 5-day training. In particular, we have a 2-day force training class that we do with Dilip Shaw. We cover measurement uncertainty, force training, measurement errors, and we go through how to really create a whole CMC budget. In the earlier slides, I showed you repeatability studies. Those came from one of our force training classes. So, if we look at element number 5 in the essential elements, documentation. Each step in the chain must be performed according to documented and generally acknowledged procedures, and the results must be recorded. Per section 5.4.1 of ISO IEC 17025, the laboratory shall use the appropriate methods and procedures for all tests and or calibration within its scope. The importance. The calibration must be performed using an acceptable and agreed upon calibration method or procedure, contract review. The result must be provided in a report with necessary information. So when a customer sent us a cell without an adapter, we called them, particularly in that the example above where I showed an 1.5 inch to a 1/2 inch thread depth. What could go wrong? Well, procedures not validated that do not cover all parameters and ranges, partial or limited calibration. This includes software. So you send your force transducer off to a manufacturer, and it's a 150,000 pound transducer, and they calibrate it. They only apply 50,000 pounds of force and interpolate the rest. Now that's an example of you're guessing. It needs to be tested. So what else? Results not reported accurately, clearly, unambiguously, and in accordance with any specific instructions in the calibration method. Again, someone could give you the calibration report that says it's NIST traceable, where they did a shunt cal instead of actually applying a known force. This is pretty bad. It does happen. So after dealing with documentation, the next essential element is going to be calibration intervals. 90 days, 1 year, 180 days, 3 years. What is your risk level? We've had proving rings come back 20 years. We certainly don't recommend having a 20-year calibration interval, though we have had proving rings come back 20 years and repeat, just as if they were here 20 years ago. They were stored, they were kept well. For whatever reason, they repeated. We certainly do not recommend that. We recommend you select the interval that best suits your measurement uncertainty needs. Calibration intervals. Calibration must be repeated at appropriate intervals. The length of these intervals will depend on a number of variables. Uncertainty required, frequency of use, condition used, stability of equipment. If we look at ISO IEC 17025, section 5.10.4.4, it states a calibration certificate or label shall not contain any recommendation on the calibration interval except where this has been agreed with the customer. Contract review. The importance of this. If inappropriate calibration intervals are used, the reliability of results reported are questionable. Profitability can be reduced if intervals are too short. What could go wrong? Well, inappropriate intervals can result in unknown drift, increased measurement uncertainty, MU, and incorrect claim of measurement uncertainty reported. So if I think I'm going to have a drift of 0.5%, I let this interval run 2 years, and it's really 0.25%, and I'm claiming a CMC of 0.1, I'm not claiming the proper measurement uncertainty. Note, for ASTM E74 and ISO 376, these are standards that actually address recalibration intervals. If somebody has either standard, they can look at them. ISO 376 is typically 26 months. ASTM E74, if you look at section 11.2.1, that specifies the appropriate interval. That basically says for Class A devices, over the calibration range, the percent change has to be less than 0.16%. And for Class AA devices, the change has to be less than 0.032%. And if that criteria is being met, a 2-year recalibration interval for that standard can be applied. Number 7 is measurement assurance. Measurement assurance practice is put in place to monitor a testing or calibration process and to ensure the calibration status of equipment. Reference standards or reference materials used in a measurement process. A measurement assurance program needs to exist for each step in the measurement hierarchy to ensure the competence of measurement results. Okay, so what do? How do I ensure I'm making the proper measurements? I alluded to this earlier with proficiency testing. There are several service providers out there offering this service. Interlaboratory comparisons, ILC. You can compare, you can check EN ratios. This is on the sheet. If you send us an email and ask for a copy of that spreadsheet, we'll gladly give it to you. Intermediate checks, SPC. SPC is statistical process control. In fact, we believe SPC is so important that we offer a full-day class on it. This is something that you can monitor what's going on in your laboratory. If you happen to have an out-of-tolerance condition, SPC more than likely is going to tell you when the artifact was last good. So if on Sunday I check my artifact and it's good, and on Wednesday I have an outer tolerance condition, now all I really have to do is look at all the calibrations performed between, really whatever my last check was on Sunday and Wednesday, instead of having to look back on a year or maybe 2 years of data. So per section 5.5.10 of ISO IEC 17025, when intermediate checks are needed to maintain the confidence in the calibration status of the equipment, these checks shall be carried out according to a defined procedure. Consequences from lack of measurement traceability. Well, we all have profit, risk, and loss. How much risk can you take? Without all 7 elements in place, your measurements are not traceable. There's no way to argue this. People say, hey, it's traceable to NIST. I bought a torque wrench on eBay that said it's 0.4%. Actually, it said it was 4% and said it was NIST traceable. I got a little piece of paper that said it was. No statement of measurement uncertainty, nothing else, no going back to the company, no certificate, scope of accreditation, none of this. So all 7 elements need to be in place. Generally, an accreditation body is going to come out and audit to make sure all of those 7 elements are in place. What measurement errors do? They raise the risk for product failures, false accepts, and false rejects. So false accept is a consumer risk. I pass something that's actually bad. A false reject is when, okay, I'm failing something that's actually good. I'm redoing the work. So either way, it's going to cost the company money if you have a false reject or a false accept. We often bear the burden of a false reject because we do not want this to end up with at the consumer level where the impact can be quite large and the liability can be huge. Liability. If you are taking the work, are your measurements detectable? Any element measurement traceability chain? The answer is no. So brief review, and then I'm going to answer some questions. This 7 essential elements of traceability, reference to International System of Units, an unbroken chain of comparisons, measurement uncertainty, competence, documentation, calibration intervals, measurement assurance. This one I put in there for my own sake because metrology is not meteorology, even though Google Gmail tells me metrology is not a word. Anyone using Gmail hopefully get a little chuckle about that. Do back and forth with NIST, some other agencies, and type in metrology, and it wants to autocorrect for metrology. In fact, I sent an email out once to NIST, and they asked me how the weather was the next time I called them, so I get a bit of a chuckle to that effect. So, wrapping up, if you do not know how the instrument should be calibrated, what should you do? I hope everyone realizes the importance of this. You should contact the user and find out how the MT&E, measuring and tested equipment, is being used. This is element number 5, documentation contract review. So now, for those that are staying on and have questions, I want to thank everybody that listened throughout this whole webinar. It will be available on demand. It is available for download on our website. If you want to learn more, please visit www.mhforce, read our blog, and sign up for our newsletter. Our newsletter has several articles on everything to do with force. And I will also give a quick promotion out. We are featured in this month's Test Engineering and Management magazine. And there's a lot of information on measurement errors in there.
Thanks, Henry. We are about out of time, but let's try to ask one question here for our Q&A portion. And again, if you have a question, please submit it by entering it in the box at the bottom of your screen, and our sponsors will do their best to address those questions after today's presentation. So Henry, let's try to get one in here. Can you elaborate on why different adapters are affecting calibration?
Okay, so that goes back to some statics, a lot of engineering. It's the cell may receive a different stress level with different adapters. If you have half engagement on something, that actual element in there may be stressed differently. You go back to Young's modulus, the stress-strain diagram, and some other basic things. Basically, it's just going to tell you that you apply a relatively known force to something, different adapters going to pull it or give that element inside a different stress. This would be something I'd say maybe come to the force course, or maybe look at strain gauge. There's a book published, Strain Gauge Theory and Design, that gives you a lot of information on this particular topic. So there was a couple other ones there, Billy. Do we have time for one or two more?
Well, we're out of time, but you'll be able to address these questions that came in after the presentation. So we're going to have to conclude it here. Again, if we didn't get a chance to answer your question today, our sponsors will do their best to address them after today's presentation. Our thanks to Henry Zumbrin and everyone out there for joining us. And just a reminder, this webcast will be available on demand at www.techbriefs.com for the next 12 months. Have a great day.
All right. Thank you, everyone.